Financial Modeling, Topic 2, Estimating Asset Risk, copyright Lou Gaddis. In this topic, we are going to estimate standard deviations for a number of assets. These standard deviations are important in finance because we're using to construct optimal portfolios that use risk return or risk return optimization. We need standard deviations for things like planning for retirement. We need to know the volatility of our assets to know the probability that we'll have enough money. To value equities and options and forecast cash flows, we'll often need standard deviations. In this lecture, we're going to compute asset return variance as standard deviation without using functions, and then we'll use Excel's functions to get a better understanding of them. We'll then scale standard deviations across time, so if we have monthly or weekly standard deviations, we'll move them to daily or annual. We'll compute volatility using a model called EWM, exponentially weighted moving average volatility, which accounts for autocorrelation of volatility. We'll also talk about GARCH estimates, which are very close to EWM. And we're also going to compute implied volatilities using Black-Scholes. So if we grab this data and put it in Excel, what you see, these are from adjusted closing prices for IBM, J&J, Goldman Sachs common stocks, IOO, which is a global S&P 100 fund, SPY, which is a S&P 500 index fund, EFA, which is a developed nations fund, so EAFE indexed fund, and EEM, which is an emerging market equity fund. And the data is from 11/3/2004 to 2/2/2014. I'm sorry, 11/3/2014 to 2/2/2004. And I already calculated returns from that data just using simple discrete returns from Yahoo Finance. So let's just calculate the means, the mean monthly return for these assets. So if I take the average and then take the average times 12, you can see that IBM had a monthly mean return of 66 basis points and an annualized mean of 795. And you can see that IOO had the lowest return annualized, and the highest would have been emerging market stocks. Now, if we're looking at these assets, we might want to say, well, which was the riskiest asset over this period of time? What you could do is look at these returns and say, well, this one looks pretty risky. The first period, it was a little bit below its mean. In the second period, J&J was way below its mean, had a negative 13% return in October 2014. But then it was pretty calm, although there's some pretty big swings in there. Goldman Sachs looks like it's consistently different than the mean, +3, +3, +3, +3, +4, -2, -1. So that's some pretty big swings on a daily basis, given that the monthly mean was 97 basis points. So to get a measure of how risky these assets are, what we're going to look at is we're going to compare the mean to the periodic returns and see how they deviated from that mean as a measure of risk. Now the easiest way to do that would be to get a graph of this data. So I'm going to go to Data, Data Analysis, Histogram, and I'll get a histogram of IBM's returns. So in the input range, I'll put IBM's returns. Since I included the label IBM, I'll click on Label, and I'll chart that output. So this histogram puts the returns in bins. In other words, it counts how many returns were greater than 9.9%, how many returns were less than 20%, and then these are bins. How many returns are, say, between -2% and +0.78%, and then it would graph it. So at 130 months of data, and looks like about 30 of the observations, actually 31 of the observations, were between that negative or that 0.78% to around -2%. So that's our mean. Our mean was 0.66%. So here's our mean. But you can see there's quite a bit of dispersion around the mean. It had a lot of really bad days and a bunching of better days. So what we do is to measure the risk of different assets, we can compare these histograms. And if one had more outliers, right, we can say, well, that's riskier. If I expected 66 basis points on IBM, this looks like there's a pretty good chance you're not going to get 66 basis points. If this were a risk-free asset, all of them will be lined up on one bar here. So to compare this dispersion across assets, we need a measure of this spread. All right, and the measure of that spread we're going to use is something called standard deviation. Standard deviation tries to fit a curve, looks like a bell. It's a symmetric single-peaked curve. It tries to fit it across the data, and then it picks a metric called standard deviation, which measures how fat this bell is going to be. So a bell that would be a standard deviation that would be larger means that this curve has a fatter distribution. Okay, if the standard deviation is less, it would have a thinner distribution around the mean. So just a little discussion of standard deviation. You can think of standard deviation a couple of different ways. One, 18th century statistician flipped coins, and those coins he flipped, he then recorded a series of 12 flips, and then did it over and over and over again, 12 flips. And what he found is what you would expect is about 20 to 25% of the time. The most likely outcome is you get 6 heads. So this is a graph of 6 heads, a histogram, out of 12 flips. And sometimes you get 7 heads, 5 tails, 8 heads, 4 tails. And every once in a while, a small percentage of the time, you get 11 heads and 1 tail. And then a very, very small percentage of the time, you get 12 heads and 1 tail. So this is a measure of kind of a tendency here. The central tendency is to get the mean of 6 heads. And there's a dispersion around that mean. And then here's something called a Galton board. This is a machine in which you drop balls straight down and they hit metal pegs right here. And as the hits a peg, again, all the balls drop from the central point. As you would hit a peg, the balls go left or right or left or right or left or right. And it's most likely they're going to wind up in the middle, as the balls all, on average, go back to the center. However, sometimes a ball will hit a peg and go right, 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 and wind up in one of these bins, and sometimes it'll go left, 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 and wind up in one of these bins. So what appears to be a chaotic movement of a ball, I can never predict exactly where a single ball is going to wind up. When you drop enough balls, there's a lot of order to it. I can predict very closely what the final distribution of many balls, just like I can predict the final distribution of coin flips. So the initial flip, or one flip, is complete chance and not predictable. Many flips are very predictable. If one ball is unpredictable, many balls are predictable. So this is the idea that you can go from chaotic random occurrences to a very much of an orderly outcome. And that's the name of this title. The title of this video here is From Chaos to Order. Actually, if you're interested in these topics about the normal distribution and these types of discoveries, here's a reference of a book. It's called Against the Gods, A Remarkable Story of Risk, which talks about a lot of these developments. Anyway, so people took these this type of finding that we have this distribution of these random processes, just like the balls, just like the coin flips, and they applied it to things like human height. And they saw that, well, the average man, if I just look at the 1,000 men and look at their heights, they'd have this distribution, and they fit a curve to this observations of these physical items or physical processes. And they developed mathematics that if fitting a particular curve to a lot of these occurrences, they figured out a mathematics to predict. And they called this curve a normal curve, or a normal or Gaussian distribution, also called a bell curve. And if you assume something's normal, the mathematics of the curve would say, and you estimated the dispersion, how wide the distribution is, called the standard deviation, you can then make statements like, if the distribution is normally distributed, 68% of the time you're plus or minus 1 standard deviation of the mean. About 95% of the time, if I add up these four numbers, 34, 34, 6, 13, and 13, about 95% of the time, you're plus or minus 2 standard deviations of the mean. So for example, the average man is 5'10 with a standard deviation of 3, which means that if I take 5'10 and add 3 inches, that would be 6'1, and I subtract 3 inches, that would be 5'7. We would predict that 68% of men fall within a range of 5'7" to 6'1", and we'd find that 95% of men are plus or minus 6 inches of the mean, and 99.8% of men, right, the tails here, anything greater than 3 standard deviations is only 0.1%. Anything less than 3 standard deviations away from the mean is 0.1%. So about 98% of the time, or 98% of the occurrences will be plus or minus 3 standard deviations, or 9 inches. So it'd be saying, say, 6'7" man, roughly, or 6'6". So if you assume an asset is normally distributed, just like human heights and physical phenomena like intensity of light and weather and rain and snowfall and things like that, and corn flips, finance kind of hijacked this math, or kind of borrowed it, and they'd said, well, if I assume that asset returns are normally distributed, well, then I can answer a lot of questions. And this started to be applying in the last century, that they applied the mathematics of normal distributions and Gaussian distributions to finance and allowed them to solve problems like, how do I value an option, which has been plaguing financial theorists for a long time. But they found out, well, if I assume asset returns are normally distributed, I can borrow the mathematics of a couple centuries of work to solve those problems, and also help develop models like capital asset pricing model, CAPM. So if you assume asset returns are normally distributed, which is a little risky because asset returns are not a physical phenomenon, right? Everyone, you rarely see over a 7-foot man or under a 4 or 5-foot man, but you do every once in a while see a minus 100% return in a stock, or a 300% return in the stock. So it might be like seeing a man that's 3 times the size of an average man, say a 15 or 18-foot man. But we use the mathematics and just kind of know that it's kind of a dangerous assumption, but it's an interesting model and way of looking at it, and maybe it informs us and allows us to make some decisions. But we are kind of nervous making that decision, and should always use the results of any models that assume normality with a little bit of caution. So how we specifically measure the standard deviation is it's the square root of another measure called variance. Variance, inside this square root here, is the average square deviation from the mean. So if I look at each one of my observations in each period, subtract the expected or mean value, square that, divide by the total number of observations, you get a simple average of the square deviations. So if I go back to my worksheet, for IBM, I'm going to calculate the mean of IBM in period 1. So I'll take the return of IBM in the first period minus the mean return for IBM. I'll go ahead and put a $ in front of 2 because I want to copy that formula. That will anchor it. And I square that deviation from the mean. So in the first period, IBM was negative 0.68. It's expected to be 0.66 according to its mean, so it's quite a bit below its mean, about 130 basis points or so. So we square that, and that's the square deviation from the mean. So now I can copy that down and copy that over. I have now the square deviations in every period for every asset. If I take the average of that column, I see that IBM has an average square deviation of 29 basis points, and there are the rest. Now the reason why we square it, well, if I go back to my histogram, if I were to just, here's my IBM, 66 basis points is the mean. If I were just to calculate the average deviation from the mean, so just take all these observations and take the average deviation from the mean, by definition, the mean was calculated such that the average deviation from the mean would be 0. So in other words, if I were to just make this, take the square out, all these numbers would turn out to be zeros. So for all the deviations not to cancel out, you could either square them. That'll make sure the negative turns all the deviations positive. The other alternative is to take the absolute value of all the deviations and calculate something called the mean absolute deviation. But it turns out that most people like to square the deviations to get to make sure they don't cancel out and get 0. And it also makes things easier when we do some other mathematics on these values of standard deviations. It's easier to deal with a a squared value than it is an absolute value if you want to do further math, like take a derivative or integral of it. I'll then take my square root, take that to the 1/2 power, and that is the monthly standard deviation. The reason why I take the square root is we had to square that data in order for it to not cancel out, but then we can't compare variances really with means, since one is kind of a squared return measure. So we take the square out by taking the square root. So this is the number we really care about. This is the number which we can apply to that bell-shaped graph and then talk about the mean versus the standard deviation. We want to use standard deviation, not variance. Now we could use Excel's functions. Var P, which is the population variance, and I just take on the returns. So population variance does exactly what we just did up here. You get the same values. In the P, a lot of people ask what the P is. The P stands for population. If I do take the P off, all right, I will get a value. That would be the sample standard deviation. And what you'll see is the number is just a slightly higher with these number of observations. And the only difference between a population and a sample variance is that in this case we had 130 observations, so we just add up these 130 numbers and divide by 130 to get a population variance. To get a sample variance, you add up these 130 deviation squareds and divide by n minus 1 observations. We divide by 129, so we get a slightly higher number. And the intuition between sample and population is we don't really, if it's a sample, it's not the full data set, we don't really know what the mean is. Therefore, the standard deviation is probably higher when we look at deviations from the mean. There's a little discussion. I have a link later to talk about sample versus population. We probably should be using sample, but I'm going to use population in this case only because it ties back to these data. In finance, usually it doesn't make a difference because we have so many observations. The difference between dividing by n or n minus 1 observations has a little effect. So let me take the standard deviation, STD-EVP. And there are my standard deviations. Again, they tie back to what we did. Now these are the monthly standard deviations and the monthly variances. We can scale variances across time and say, well, what is the annualized variance? We can just multiply it times 12. But when we say, what is the annualized standard deviation? We take the monthly standard deviation times the square root of 12. That's called the square root, or we use the square root rule for scaling standard deviations. And the way to think about it is, well, to go from variance to standard deviation, we have to take a square root. The other way to think about it is when we scale standard deviations across time, and if you assume these asset returns are independent, the risk does not go up by 12 times, because it's just likely to go up or down. Or if it goes down, it's not likely to go down again. It might just pop back up. So the risk is less than just multiplied times 12. It's the square root of 12. Again, there's a link at the end to kind of have a little discussion of that. So these are my sample, or my full 130-month standard deviations on monthly returns that have been annualized. And now you can say, okay, Goldman Sachs is clearly the riskiest asset over that period. You know, it was just hard to look at this or look at histograms, we have this measure of dispersion. So when you scale volatilities or standard deviations across time, we always multiply times the square root of time for making it larger. So if I'm going from monthly to annual, I'll multiply times the square root of 12. If I have annual and I need monthly, I'll divide by the square root of 12. Or if I say have annual and I want daily, I'd divide by the square root of the number of days in my year. And we usually assume 252 trading days in an equity market. So I now have the mean and standard deviation. Say if I was looking at the S&P 500, which my guess is it has about an expected return of about 7%. Using CAPM, there's about a 2% long-term treasury rate, 10-year, and I think there's about a 5% market risk premium. So I think the U.S. equity market has about a 7% expected return, and the historical volatility is 16% over a long period of time. So if I make a huge assumption, okay, again, I'm always a little nervous making that assumption, but if I make the huge assumption that the S&P 500 returns are normally distributed, we write that the expected return is distributed normally with a mean of 7 and a volatility of 16. We can then make our statements based on our graph. We know that 68% of the time will plus or minus 1 standard deviation. So if the mean is 7, 68% of the time is between 7 plus 16 or 7 minus 16, between minus 9 and 23. 95% of the time is plus or minus 2 standard deviations, so plus or minus 32%, minus 25 and 39. And 99.7% of the time, I'll be plus or minus 3 standard deviations of the mean. So it's between negative 41% and 55%. And again, this is assuming asset returns are normally distributed according to our distributional assumption. Just a little side note here. In Excel, if you want to calculate either the number of standard deviations given a confidence interval or a confidence interval given standard deviations, you can use 2 Excel functions. So in other words, if you want to know, well, how many standard deviations are in the confidence interval, 68%. Or if I said, well, what is the confidence interval, this 68% of 2 standard deviations or 2.5 standard deviations? In Excel, I'll just click on the cell here. I'm going to use this calculation here, that if I'm given the numbers of standard deviations, we call them Z standard deviations, that variable Z. The confidence interval is given by this formula here, 2 times norm S dist of the 3 minus 1. The reason we have to multiply 2 in this equation is Excel statistics or one-tailed test. We're looking for a 2-tailed confidence interval. So Excel can tell us that we should be 99.73% confident that a normally distributed variable will be between plus or minus 3 standard deviations. Or again, use this function, minus norm S inverse, and then inside the function there of the norm inverse is 1 minus 99.73 divided by 2. We'd see that is the 99.73%. So again, we could change these values and say, how confident are we of being a half a standard deviation? Well, 38% of the time, you'll be plus or minus 1/2 standard deviation. All right, also in this lecture, I just want to warn you, I use the word volatility a lot, and it's synonymous with standard deviation. So when I'm talking about volatility, I'm talking about standard deviation. Also, I want to talk about how standard deviations move over time. So if I want to look at how standard deviations move over time, I can calculate something called a moving average volatility. So I'm going to go down to my spreadsheet, and I'm going to use my S equals STDEVP. And I'm going to highlight just the 12 latest returns for IBM. So it's really just December 2013 to November 2014. That's my monthly standard deviation over the last 12 months. I'm going to multiply that times the square root of 12 to annualize it. And you can see the annualized volatility over the last 12 months for IBM is 18.67. And then I can copy this. So this is a trailing 12-month annualized volatility right now. To get a moving average 12-month volatility, I'll move it. So now each one of these numbers is going to be the last 12 months volatility. I'll stop it before I get to the bottom because I'm going to run out of data. So if I take a look at this series here, I'm just going to graph that real quickly. This IBM's 12-month moving average volatility. And then I'm just going to make this a little smaller. And then let me just add my x-axis. I'm going to right-click, select data. Let me put in the horizontal axis. I'm just going to grab the dates right next to them. And that'll put them in chronological order for me, which is make it look a little nicer. So now we have IBM's 12-month moving average volatility. So in other words, this value here is just the last 12 months. This value here, say in 2009, represents the 2009's volatility. So each data point is looking back 12 months. So this is what makes volatility estimation difficult. If you needed the volatility for IBM for the next month or next year, should I use the long-term for historical value of 18.5? Should I use what it's been recently, more like 18.6? On the other hand, it actually has been running very calm up until 2 months ago, because 2 months ago they had that 15% drop. So it's actually been running for the last few years really closer to 15. All right, so what we find, researchers have found, is volatility has some autocorrelation. So what that means is if times are volatile, they're likely to stay volatile, a little more likely to stay volatile. And if asset returns have been relatively calm, they're a little more likely to stay calm. So we call that autocorrelation in volatility. All right. Now we have a model that accounts for that. And so what this model I'm going to show you does is that when it looks at this data, we think that this data may be more indicative of the future than this data back here. This is the big Great Recession and crash, 08-09. So what if we can calculate a average square deviation from the mean, where I weight this data a little more heavily than I weight this data because I think it has more predictive power. All right, that model we're going to build is called EWMA, exponentially weighted moving average volatility. All right, remember, this is our formula for standard deviation. It's the square root of the variance. Variance, in our case, we took 130 returns minus of IBM, subtracted its mean in each period, squared it. That was our column we created. And effectively, for 130 observations, we just multiply each observation by 1 over 130. So each observation, that's about a 0.8%. Each observation is weighted about 0.8%. It's all equally weighted. However, research has shown that the volatilities are autocorrelated. So we think that last month's volatility deviation is a little more informative for next year's forecast than, say, 5 years ago. So the exponentially weighted moving average volatility, EWMA volatility, accounts for that. So EWMA volatility takes this formula, and it's going to take this number here, this vector. Say, think about this as a column of weights, which are now all equal, 1 over 130 in our case, and it's going to replace it with this vector of volatilities. 1 minus lambda. Lambda is just a mathematical constant times lambda to the I minus 1 over the sum of those factors. So I'm going to use a constant of 0.98. I got that from JP Morgan risk metrics document that says the optimal decay factor or predictive factor, or lambda, for estimating U.S. equities is 0.98. And I'm going to take that and I'm going to calculate an EWMA vol that weights the more recent data a little higher. So I'm going to put my 0.98 in there. And actually, let me give that a named range. We'll call that lambda. All right, so 0.98 is lambda. Let me go ahead and just link over returns for IBM. And here's the squared deviations for IBM. All right. And let me number this 1 to 130. So now I have 130 square deviations, and I've numbered my returns, and these are in descending chronological order. So this is the most recent. That's where you want to set to 1. And let me just plug in my formula. This is my I. This period is my I. 1 minus lambda times lambda to the I, which is this period here, minus 1. And I get 2%. I'll copy that down. So these are a set of weights, and if I were to graph these weights, what you'd notice is they go down. They get smaller. And they seem to go smaller in kind of an exponential function. So what this says is I'm going to weight my first day 2% and my last day, that's about 0.1 or 0.2%. So that's my set of weights I'm going to use. But there's a problem with these weights. If I add them up, you can see they don't add up to 100%. Let me get that to work again. They only add up to 92%. Okay, so we have to do a little trick to make sure you never want to do a weighted average where the weight is less than the sum of the weights is less than 100%. Otherwise, it's going to factor down my variable. So what we're going to do is a little trick to make these weights add up to 100%. We're going to take that 2%, divide it by that sum. I'm going to anchor that, put dollar signs around that sum, copy that down. And now I have a set of weights which add up to 100% and decrease in an exponential way. And these are going to be my weights that I apply to the square deviations. So I'll take each weight times each square deviation. Now if I take the sum of each weight times each square deviation, the sum is going to be my EWM variance. Right? Variance is the average square deviation. In this case, it's the probability weighted or just a weighted square deviation using these unequal weights. And I get 26 basis points as the EWM variance, which, by the way, is less. If I go over here, what is my historical variance? 29 basis points. So what's going on is the variance is less, the EWMA is less than historical because it's probably not weighting those turbulent times. Well, it's because it is not weighting those turbulent times as much. Now this is monthly variance because it's a weighted square deviation. If I take that value and take the square root of it, that'll turn it into standard deviation. So this would be the monthly standard deviation. If I then multiply times the square root of 12, I then have the annualized standard deviation. So my EWMA annualized standard deviation is 17%. Which is less than my 12-month average of 18 and less than my full sample of 18.5. So what it's saying is even though it had a really volatile month 2 months ago, that's why this popped up, it's weighting this data a lot more than this data, and it's pulling down the average square deviations. So my full sample is about here, 18.5. Last 12 months is 18.7 because we had a really volatile month 2 months ago. But EWMA is more like 17. So these are ways of estimating volatility. Now I use the lambda of 0.98. Let's think about what that means. One way to think about it is if I move the lambda down, what you'll see is the prior months is 1 minus lambda. So one way to think about lambda is it tells you, if you take 1 minus lambda, it's really the weight of the last month. So as lambda goes down, you weight the most recent data even more. As the lambda approaches 1, let me put in 0.9999. Now the weights approach equal weighting, and actually my volatility becomes the simple average standard deviation that we calculated before. So as we move this away from 1, we're starting to weight the more recent data more. And risk metrics was a division of JP Morgan that would forecast optimal decay factors based on historical data for different markets. And I assume the way they did that is they create a data set like this, and what they do is they calculate, say, an EWMA vol every single month over the last 10 years using trailing, some amount of data, and they'd have some kind of solver routine that says, well, what lambda historically has been the best predictor for the next month's volatility. That's, I assume, how it's done, and that is 0.98. All right, we're not going to worry about how to calculate it for now. We're just going to be exposed to what that is. And the last volatility we're going to look at is Black-Scholes implied. Now, Black-Scholes is an option pricing model. It's an option pricing model that assumes asset returns are normally distributed. And a lot of people use it to value an option to find, say, a cheap option or expensive option to find some investment opportunity. But another way to use this model is to use it to estimate the volatility of an asset. So let's grab, these are the Excel's, our VBA code for BS call. That's the Black-Scholes call function, and BS put, Black-Scholes put function. I'm going to copy those two functions. I'm going to go to Excel, either hit Alt F11 or go to your Developer tab, Visual Basic. I'm then going to insert a module and paste. So I have BS call, BS put. The parameters for BS call is you need the stock price, the strike price, the volatility, the interest rate, the maturity in years, and the dividend yield. This is the mathematics for Black-Scholes. I'm going to then close that. And I have data that I collected for an option on IBM. So on this option, matures in a little over a year. 1 year interest rate was about 20 basis points. IBM's dividend yield was about 2.5%. Current stock price is 141. Strike is 140. And the option was trading for about $8.48. I'm going to insert my Black-Scholes function that I just created. So I'm going to click on my function insert icon, go user defined. There's BS call. I'm going to put in the stock price, 141, strike price, volatility, which is just a guess right now. I put in 20%. Interest rate, maturity in years. I'll slide this down and pick up the dividend yield. And I get Black-Scholes price of $10.33. Now the market price is $8, so if you're a trader in an option, you might believe that this is an undervalued option, so maybe you'd buy it. But that's not what I'm interested in. I'm just going to make the assumption that if on the average trader is using this model to value options, the option reflects the parameters. The option value reflects the parameters. The parameters are pretty well known, except for one, and that is volatility. So you notice that, well, maybe the option is not undervalued. Maybe I'm just forecasting the wrong volatility. What if I put 19%? Okay, without the price drops to 9. What about 18%? Price drops to 920. What about 17%? 865. So around 17% is the value you need in the volatility to make Black-Scholes give you the value of the option. I'm going to use goal-seek to get a more accurate value for that. So I'll do data, what if, goal-seek. I'm going to set the BS call price to a value of 848, which is the market price, by changing volatility. All right, so at 16.71% volatility, or standard deviation, the Black-Scholes model will give you the market price. So we call that the implied volatility of IBM's returns over 1 year. So that's the life of the option. And studies have shown that this is a good predictor of volatility, better than just, say, historical moving average volatilities or other estimates. So for IBM, what we did today is we calculated a full sample volatility. We looked at the last 12 months. We looked at EWMA with a 98 lambda. And we got a BS call implied vol of 1671. Right. These are estimates of volatility. My own personal preference, I prefer to use an implied vol if at all available. If there's, say, several options traded, some liquidity in the option, it seems like the price has enough volume, or the option has volume. I'll take an implied of several of the options, take an average, and that would be my estimate for volatility. Otherwise, I might default to, say, an EWMA. One model we haven't talked about, and I'll get to it in a later lecture, is GARCH. All right, so I'll spend 1 minute talking about that. GARCH is similar to EWMA in that it accounts for the autocorrelation of volatility, but it also accounts for another empirical finding, that there seems to be long-term mean reversion of volatility. So the way to think about GARCH, which stands for Generalized Autoregressive Conditional Heteroscedasticity, that's why we say GARCH. It's a lot easier. GARCH might give an estimate that's close to this, based on your parameters, but if this value is, say, lower than the long-term average estimate of volatility for IBM, GARCH may have this number be, say, a little bit higher. So the idea of GARCH is it accounts for autocorrelation, but it also has a mean reversion term that will adjust it a little bit towards the long-term mean volatility over time. While we're talking about volatility and implied volatility, I'll just mention the VIX, or sometimes it's called the fear index. The VIX is an index that's published daily in financial papers and websites. And what it is, and last week was 17.55%. That is actually an average implied volatility of a basket of options. Specifically, it's a basket of 1 month. Our options that mature within 1 month of the S&P 500. So it's an estimate of an estimate of volatility, standard deviation annualized, over the next month for the market. So they call it the fear index, or just call it by its ticker or symbol, the VIX. So hopefully you've learned how to estimate volatility. We need one more volatility estimate. That'll be GARCH. That'll be later. Here's a little discussion of population versus sample standard deviation. And hopefully we now can estimate volatilities that we need for option pricing and planning for retirement and creating portfolios and valuing equities. And we did that by looking at historical values, scaled historical values using the square root of time rule for volatility, computed moving average volatilities, EWMA, and Black-Scholes implied. If you want some more information, here's some good links on, say the standard normal distribution, the book I mentioned, Against the Gods, time scaling of volatility, and so on.